Hello, we can start the second part of the tutorial. So, as we mentioned, the tutorial is on fraud detection and user modeling, and as Alex said in the beginning, these are sides of the same coin, right? If we know how our users behave, we can figure out what the majority of the users behave. This is normal. The minorities are probably strange, and some of them may be fraudulent. So we mentioned that there are three parts of the tutorial. The first is algorithms that operate locally on subgraphs, and that's what Leman presented. We started talking about global methods which use propagation. If I am conservative, my friends are probably conservative, right? And later, Alex will talk about global methods that use matrix factorization. There is a lot of connections between all three parts, but we broke the methods down into these three groups for easier presentation. So we saw that belief propagation can help us spot normal behavior and can help us guess labels, right? As we saw, if this person is from Stanford, then this person from Stanford, so all this group is probably from Stanford, right? Oops. Right? And if these people are from New York, then this probably blue cluster, this blue cluster is from New York, right? And we can propagate the labels like that. So now we'll see how we can use belief propagation to spot anomalies, the third part, abnormal behavior. So here, this is the work with Kat Singh, with colleagues from Tsinghua University. And the data is from Weibo, who follows whom. So here we have about 100 million people who follows whom. And for every node, we have two numbers. We could have as many numbers as we want, as many features we want. Let's focus on these two. For every node, we have the out degree. So if you follow 20 people, your out degree is 20. The axis is logarithmic. And for every node, we can compute the hubness score, the left eigenvector, as we said, from the Hitz algorithm, right? This is logarithmic, right? So there should be correlations. If you follow a lot of people, you should be a good hub. And these people are good, right? You should be a good hub, right? So it's expected that there will be a correlation between high hubness score and high degree, right? So now the question is, what are the patterns and what are the anomalies, right? And we notice that, for example, here, we have people who have high degree, 300, but their hubness is 10 to the minus 6, as opposed to 10 to the minus 3, that it should normally be. So this is suspicious, right? And this is the idea of the algorithm. We try to find groups of people, right? We try to find groups of people that deviate from the typical behavior. Let me explain. This is a heat map. So every blue dot is one person, right? If a lot of people have exactly the same degree and exactly out degree and exactly the same hubness score, then there is overplotting, and we represent them as blue if they're about 80, as red if they're about 100,000, and so on. So this is a heat map. This means that red means that there are a lot of people with this degree, 20, whatever this degree is, and high page rank and high hubness, right? We can also, this is a directed graph, we can also create the symmetric plot for the in degree of every node, right? So if 2,000 people follow you, then your dots should be around 2,000, somewhere here. And if your authoritativeness score, you're using the Hitz algorithm of Kleinberg, your authoritative score is 2 to the minus 9, then you should be somewhere here. And again, if there is overplotting, we have the heat map, right? So again, we see a correlation, a J shape, a hockey stick shape, right? And deviations. So deviations are probably suspicious, right? Not only that, but we can also figure out who is, we can figure out a specific person. So this person, this is a fictitious example, of course, right? We don't know who is following, right? Suppose that this person is following these 4 people, right? Again, fictitious example, one of them is in the audience, right? And we know that, let's say, Alex has such and such in degree and such page rank. Jawei Han, fictitious example, such and such in degree, such and such authoritativeness. I'm sorry, not page rank, authoritativeness, and so on. So we see that the fictitious Obama user is following people whose dots are following along the J shape. So all the followees seem to be normal. They fall on the J shape, right? Therefore, probably this is an okay account because all the people he or she follows, right, he in this case, fictitious case, they are in the J shape, right? On the contrary, so if this is what the followees are, then the follower is probably okay, right? Now let's see if we pick another account, so we don't know the name, right? So in this example, this account follows all these people. This person does not even, this followee does not even have a figure, right? If the followees are all of them nicely concentrated, the red boxes don't show here. Let me see if the next, yeah. So there are all the followees here. So the orange egg is somewhere here, Death Star, right? The Darth Vader is somewhere here, right? If all the followees are away from the J shape, that's suspicious. And actually the idea behind the cat-sync algorithm is that followees, a group of followees is suspicious if they are abnormal, which means far away from the J shape or far away from the typical, the mass behavior, right? And also concentrated. Notice that normal followees are spread out, right? So this honest person is following some very high popularity person, huge in degree, right? Some low popularity person, yeah, because they're close friends, but the friend does not seem to be famous, right? While here the followees of a bad account are nicely concentrated in lockstep behavior, as Leman mentioned. Bad behavior, fraudulent behavior usually is concentrated, is created by a script or something, and there is not a lot of variation. So this is the idea, how we can spot, given a node, we can figure out the followees of this node, and if the followees are far away from the mass and nicely concentrated, then we give an abnormality score. We won't go over the details, but the idea is that after we apply this cat-sync algorithm, which penalizes groups that are coherent and far away from the rest, then we see that this blue stripe disappears. They were all deemed as fraudsters by the algorithm, right? And some of the red crosses here, there are a few red crosses, some of the red crosses disappear too. And the same happens for the other plot, right? This is the in degree versus authoritativeness plot. We see there is a J shape, the hockey stick shape, but there are some things sticking out. The algorithm, the cat-sync algorithm, KDD 2014, right, blanks them out and say they're all suspicious, don't ignore them, right? Once we ignore them, we see a more clean hockey stick shape, right? People might say, oh, what about these guys? Oops, sorry. What about these guys? Probably we should catch them too, but we didn't, sorry, right? Yeah, so this is, this illustrates exactly the phenomenon that we mentioned before. Groups of bad people usually are far away from the rest, from the mass, and synchronized. Again, feel free to ask questions anytime, right? Okay. So this is precision accuracy experiments, so bigger is better. So cat-sync alone has 0.7 accuracy. Compared with other methods, it's much better. And actually, the spot algorithm, which uses the text of text information, is complementary. And combining spot and cat-sync, we get even better results. Here are the precision recall results, right? There was manual evaluation. Some people, so the algorithm returned several hundreds of users as suspicious, and people, humans, sat down and said, yes, this is suspicious, this looks strange, this account looks okay, and so on. So then we had ground truth, and the precision recall, higher is better again. This is the ideal point, 100% precision, 100% recall. The red curve is cat-sync alone, so it beats everything else. Cat-sync with text information, with a spot algorithm published by other colleagues, gives even better results. That was for Twitter data. This is for Tencent Weibo data. So for two different data sets, the algorithm works well. We continue. This is a different algorithm. So we now have, if somebody could please close the door. There is a noise outside. Thanks. Thank you. So this is work from Stanford, Hector Garcia Molina and Zoltan Gyongi and colleagues, Jan Petersen. So they say, okay, page rank is very good, right? And there is this walk around and then fly out and you fly at a random node. What happens if we know that several nodes are bad because they try to sell Viagra, they try to do this and that, right? Nebulous goals, right? Suspicious goals, right? And we know that some nodes are honest. Usually EDU nodes are honest because very rarely EDU college pages, university pages point to bad things, right? So if we know that this is an honest web page and this is an honest web page, what else can we do? How can we exploit this information? And it turns out that we can do a random walk with restarts, as we did before. But instead of walk, whenever it's time to fly out, we don't fly out to any of the billion available nodes. We fly out to one of the trusted nodes, one of the purple trusted nodes. This way, the random walks stay close to the purple nodes. So nodes that are close to purple nodes get high score, and the others get low score. And this intuitively makes a lot of sense, right? Because here is a little click, this artificial graph, of course, right? We plot it ourselves, right? This is a click, everybody points to everybody else. This is probably bad people, right? But no blue, honest page points to them because they're all selling Viagra or whatever, and they don't get a good score, right? So this is the random walk, starts from a purple page, move around, fly out. Instead of flying out randomly, you fly back to one of the two blue nodes. You continue the random walk, fly back, right, and so on and so forth. This is the equation. Notice it's exactly the page rank equation, but instead of having a vector full of ones here, which means fly out anywhere you want, you have a vector which has 0 everywhere except for the blue trusted pages, right? And this restricts the random walk to stay close to the trusted nodes. It turns out that this gives good results. This is, instead of guilt by association, this is trust by association. Blue nodes are good. Whatever they point to is probably good, not guaranteed good. Whatever the pointees point to is probably good too, and so on. And here are the results that they reported. The success is to have lower is better, so this is the bucket number. So for the first bucket should have ideally clean data, almost 0. The second bucket should have as clean data as possible. We see that standard page rank, the second bucket has 20% bad pages, Viagra and stuff, while with the trust rank, the second bucket has very, very few. Third, fourth, fifth bucket, they have almost no bad pages. So this is a much better, trust rank is much better than the standard page rank. And it makes sense. You restart from pages that make sense. A similar paper with the reverse idea. Suppose we know a seed set of bad nodes. We know that this sells Viagra, we know that this sells Viagra. Who else is bad? The idea is that if a page points to a red page, this is bad too. If a red page points to somebody, this is no information, because a bad page could point to a university, could point to a hospital, right? That doesn't mean anything, right? So what they said, in order to exploit this observation, what they said is, let's do random walk again, but let's do backward random walk. So instead of following the edges in a straightforward manner, we'll follow the edges backward, right? And again, we'll have fly outs, but whenever we fly out, we'll go back to one of the red nodes, the Viagra selling nodes, as opposed to any gray node, right? This gives good results, and these are the equations. Again, this is again the PageRank equation, right? Notice that we have the M matrix, which is the reversed from the adjacency matrix, right? We reverse the directionality. And S is the vector, 1 million entries, with 1 whenever there is a Viagra selling site, and 0 everything else, right? The last paper is Sybil rank, which is from the networking safety community, security community. So suppose we know that some nodes are honest. This node is honest, MIT.edu. This node is honest, nsf.gov or some government site, right? These are all IP addresses and connected, right? So who is to be suspected and who is not? So what they said is more or less like trust rank. do a random walk, do a fly out, but whenever you fly back to the honest edges. So what is the difference from trust rank? So far, this is exactly the main idea is exactly trust rank, right? Random walk with fly back to the appropriate pages, to the blessed pages. The slight difference is that instead of having a probability of flying out, they have an early termination. They say, do a random walk of 3 steps. 1, 2, 3. Okay, fly back. 1, 2, 3, fly back. 1, 2, 3, fly back, right? Instead of flipping a coin, which means you may do a walk of 2 steps, you may do a walk of 4 steps, right? They always do a fixed length walk. The result is more or less the same, and they give, like trust rank, they keep the walk close to the honest pages and their honest websites or honest IP addresses, and everything makes sense. Bad addresses have very small probability of being reached, right? Because they're far away from the trusted edges, right? So, now we'll talk about NetProbe, which in the layout that Alex presented in the beginning, this is a directed graph. We have no node attributes, no edge attributes, and no seed labels. So NetProbe works for eBay, and the idea is to try to catch the so-called non-delivery fraud. On eBay, of course, there is money exchange, and whenever there is money, there is fraud, right? So there are many types of fraud. This type of fraud is somebody, a bad guy, says, I have an expensive laptop. This is, let's say, me, and say, I want this laptop. Here is the $3,000 that you asked for the laptop, and the bad guy does not deliver the laptop, right? Takes my money and disappears, right? So how can we spot that? The input is we have a network of interactions, who sold to whom, and looking at this graph, the challenge is to figure out who is honest and who is dishonest. Feedbacks, whenever this person sells something to this person, they give feedback to each other, and feedbacks are almost always positive because negative feedback is declaration of war, right? Oh, you say I'm bad, I'll ruin you, I'll say that you're awful, and so everybody says it's good unless the other person really, really is bad, didn't deliver an expensive product, right? So now the question is, how could the bad guys game the system? How could they look honest until they get caught? So the naive solution, which is not what they're doing, is suppose I'm a bad guy, right? I will create 5 accounts in this example, right? I will give good feedback to myself, right? To my, this is Christos 1, Christos 2, Christos 3, right? So I'll give good feedback. Feedback costs, right? Because eBay says if I have to give feedback, in order for me to be allowed to give feedback for this person, I have to sell something. And when I sell something, eBay gets 10%. So feedback is expensive for the bad guys, right? They cannot give feedback to everybody at random, right? But suppose I bite the bullet and I do that, right? Then suppose that somebody sends me $3,000, I don't send the laptop, right? And everybody complains. So eBay says this is clearly a bad account, right? 20 complaints against this person. So this account, Christos 1, is shut down. eBay could easily, if they wanted to, they could easily say, who else are neighbors of this person? And say that, hey, these are more or less have the same behavior. So in one shot, they could shut down the whole network. And notice that as a bad guy, I spend a lot of money. If it's 5 people, I had 5 squared transactions, right? Each of them costing 10% of the sale price. So this expensive for the bad guy structure is disappearing. So what do? They have a brilliant scheme. So here are the bad guys that will do the non-delivery fraud. Here are the accomplices. They are not completely bad, right? These people, and these are honest users, right? So the accomplices will stay with eBay for a long time. They will interact with honest people and buy cheap stuff, right? So they get good feedback, right? The only bad thing they are doing is that they give, in unison, they give good feedback to Christos 1, Christos 2, Christos 3, Christos 4, right? So this person looks honest because 1, 2, 3, 4, a lot of good feedbacks from trustworthy people, otherwise trustworthy people, right? And this person, this account commits the non-delivery fraud. eBay shuts it down. Oops. eBay shuts it down, but that's not a big deal because if eBay looks ahead, they says this looks like an honest person, right? It has a lot of interactions. It has been with eBay for 10 years. There's no reason to shut down the accomplices, right? So this is a brilliant scheme. How can we spot it? The idea is to use belief propagation with probably the only matrix we have seen so far, actually, the only matrix we have seen so far that is neither homophily nor heterophily, right? This matrix says we have 3 types of users, and as somebody asked before, this matrix is given by observation, by us, right? So fraudsters never talk to fraudsters. It's expensive. Why bother? Fraudsters almost always talk to accomplices, except once in a while they talk to honest people to get their $3,000 and not deliver the expensive laptop, right? Accomplices talk to fraudsters and also by 50%, and also talk to honest people so that they build up credibility. Honest people mainly talk to honest people. Occasionally they talk to accomplices, right? So this is a strange matrix, neither homophily nor heterophily. Homophily would be if the big values are in black, right, in gray, big values were in the diagonal, right? Fraudsters would talk to fraudsters, that would be homophily. Now fraudsters and accomplices have heterophily, right? Fraudsters never talk to fraudsters, they talk to accomplices. Accomplices never talk to accomplices, why bother, right? They talk to fraudsters, right? Honest people have homophily, right? They usually talk to honest people. Occasionally, they talk to accomplices. So this is a complicated psi matrix, right? Compatibility matrix. But that's okay because the belief propagation we saw before can handle any propagation matrix. This is 3 by 3. It could be 20 by 20, major diagonal, minor diagonal. You pick it, right? The equations we saw 10 slides ago, 15 slides ago, will still work, right? And applying this method, we see that eventually we get... we start with a graph of people, we don't know much about them, and eventually we look at their behavior, and some of them get a little bit higher score for fraudsters. They started early, they advertise expensive stuff, right? There are signals, weak signals for fraudsters. So some nodes get a little bit of a suspiciousness score, not enough to shut them down, right? We start propagating. Using belief propagation, we propagate on the graph and say if Smith is sort of suspicious, his friends are probably accomplices, right? Because that's what the compatibility matrix says, right? And if we know that this yellow node is an accomplice, then whoever is talking to this person is either honest or fraudster, definitely not an accomplice, right? And we continue propagating labels until there is some sort of convergence, and at the end we have yellow are the accomplices, red are the fraudsters, and with high chances this is correct. We followed these accounts, Polo Chow, who is the main person behind this work, followed these accounts a week later, and most of them were shut down because there were too many complaints of non-delivery about them, right? So this is also cases. These are bipartite cores that the algorithm spotted, and as we mentioned, it's bipartite cores the telltale sign for this type of fraud. If we say bipartite core, these guys are accomplices, these guys are fraudsters, or the other way around. Now this is work with Leman Akoglu, who presented the first part, right? This is a slightly different problem. Now suppose we have people, bipartite graph, people give ratings about movies or products, but now we allow 2 types of ratings. Either we like this product, blue, or we hate this product, red. Can we find good products and bad products? Can we find honest people and dishonest people? It turns out that we have to modify the belief propagation a little bit. So now we have 2 compatibility matrices. The font is small, the details are in the paper, right? But the idea is that if we have a blue edge, then if we believe that this is honest, the product must be good, because blue is a good product, right? Thumbs up. If we believe that this is an honest person and gave a bad review, then this should be a bad product, right? So we have 2 compatibility matrices, one for blue edges, thumbs up, one from red edges, thumbs down, right? And applying this compatibility matrix, these 2 compatibility matrices, eventually we get suspicious products and suspicious users. So these are some users that are suspicious. The font does not show, but let me magnify. And we looked at the reviews, at the text of the reviews. The algorithm did not use the text of the reviews at all, right? But the text of the reviews, I'll read it out because the font is tiny, right? I want to be close to Jello, right? This is August 25, and this is by user Mujihara or something like that. October 21, I want to be like Jello, right? This another user, Manjul or something, right? Exactly the same text, several weeks later. Great app, exactly the same text. I'm extremely satisfied, exactly the same text, right? A different user, probably the same person under different account. Exactly the same day, all of them are October 23, all of them are August 25, right? So this is strong, this is a highly believable confirmation that these guys are fraudsters, right? They try to boost up this product. This product actually was a face image processing product. You give a photograph and it tries to morph it or something, but probably it was full of malware, and these people were trying to boost up the product so that other people, victims, will download and get hacked, right? The algorithm makes a big difference. This is product P1. Before doing anything, this had an average score of 2.5, which means neutral. 5 is the best, 1 is the worst, right? After we removed what the algorithm believed are bad reviews, the score went down to 1, which is bad product, right? And the same is true for all the other 5 products that were the most suspicious 5 products, right? So the algorithm makes a big difference in the scores. There is a follow-up paper by Leman and her group. It's appearing in a few days. The idea is to extend it and have a tripartite graph. So we have users, we have reviews with text, right? And we have products. So now we want to do analysis with belief propagation so that eventually we'll find bad users, bad reviews, and bad products in one shot. And of course, good users, good products, and good reviews, right? So the details are in the paper, and we are almost done. The last part is, yes, tripartite, we mentioned it. So this is actually, we're done. So the key points from the second part of this presentation is that we saw 2 powerful tools. One is random walks, which are closely related to eigenvalues and fixed points, which are closely related to singular vectors, right? We didn't mention it, but it's true. Singular vectors are exactly the authoritativeness and hubness score of nodes. And yes, and random walks can help us find important nodes, right? Importance propagation. And it can also help us find communities. All the important guys will group together, important for some reason. Another group of important musicians will group together, important scientists will group together, bad people will group together, and so on. The second powerful tool we mentioned is guilt by association, which is birds of a feather flock together, right? If I'm bad, my friends are probably bad, and so on. We don't have to have homophily. This is a very powerful tool. It can handle heterophily. If I'm talkative, my friends are silent, right? Or the case of eBay that we saw before, NetProbe, right? Fraudsters and accomplices. And it can handle more. And this is the end of the second part. And while Alex is ready to take over, I can answer questions. Yes?
Going back to your ranking examples and using random walk there, what I wonder is why is that better than simply saying that you're going to use a decayed multi-step neighborhood analysis?
Decay multi-step neighborhood?
Yeah. So instead of looking one step out for your known node, you start with your known node. Go out one step, and for those neighbors are highly connected.
Right.
The next 2 steps out are lower value, 3 steps out are
Right.
lower value.
They should, I think they're either identical or extremely similar.
But one's much more computationally efficient.
They're both computationally efficient because, well, PageRank is definitely computationally efficient. I'm not that familiar with a neighborhood analysis, but from what you say is probably we get the importance scores. Everybody's equally important, right? And then we propagate the importances. So whoever has a lot of connections suddenly gets more important, right? Which is what PageRank is doing, right? So we can discuss it offline. My guess is that they're either identical or very, very similar. And my guess is that they're all proportional to the number of non-zeros, the number of edges, which is as efficient as you can be, right? Good question, thanks. There was another gentleman? Yes?
You know, in the graphs that you're showing back the good sides and bad sides, the distribution of incoming and outgoing sort of edges is sort of uniform. So what I expect if you have a good side, like a university website,
So you're talking about trust rank, right? Or trust rank or sibling rank. I guess you're right. Maybe the bad sides that are probably here, right? They will have more cliquish behavior, while the good sides will probably not. This is my conjecture, right? So we could have additional information about the good and bad sides. But the algorithm is already extremely simple, right? Do the standard random walk with restarts, but instead of restarting from everywhere, restart from the blue nodes. And if this gives good results, then there's little motivation to try to improve. I agree what you say will make an improvement. Thanks. Okay, Alex takes over. Thanks. Thank you.
Great, thanks. So now we're going to talk about latent factor models. Of course, as before, we'll do background, some normal behavior, work that's been done on this, and abnormal. Of course, this is a huge area, so we're just going to sort of sample a few of the ideas in it and see how it applies in both of these regimes. So, of course, going back to the matrix modeling, right? We have this bipartite graph, let's say, of users and the pages they like. We should have sort of the static binary graph. And therefore, this term here in the matrix corresponds to the fact that there's an edge from this user to KDD. And this creates this general user by page matrix. As before, the hits algorithm will find the first eigenvector, singular vector, on the for authoritativeness on the right-hand side, and for hubness, the first singular vector on the left-hand side. And so what about the other eigenvectors, essentially? We're starting to ask this question of, as we consider beyond this first level of authority, what comes after that? So essentially what we have is this is the singular valued composition. It's U times sigma times V transpose. That first term, as Christos showed before, this blue term here is the hubness score. This red term is the authoritativeness score. You can look up online sort of some of the mathematical relations, Wikipedia, but this is the key idea. And this sigma value corresponds to the normalization. So we can sort of remove for a bit the sigma value, just consider the underlying terms here and unnormalize it. And think of it as general matrix factorization. So this first term might correspond to, let's say, computer scientists in some social network. And maybe that's the dominant sort of interest group in that network. And maybe the second term, though, might correspond to just liberals, right? So this first hubness and authoritativeness might only capture a subset of the interest and who the authorities are and the hubs are within the network, but there might be then secondary ones among liberals and maybe other groups. And so you can sort of take all of these different groups of authorities and hubs and say, let's look at, for an individual user, how much they are, let's say, a hub within this sort of category, this topic, or an authority for a given page on this topic, right? So each of these columns now represents some topic that's being discussed. And so you can say, look, this user seems to be into computer science fairly, a little bit liberal, not conservative. Maybe he likes music a little bit, and he really likes computer science research, ACM. And on the page side, we have KDD, right? KDD is definitely part of computer science. Maybe there's some liberals, some conservatives. It's not really into music that much, and it's definitely part of ACM. And so the inner product of these two terms, how much they each belong to each of these topics within the graph, will help predict that this is a value of 1, approximately. So you sort of can move from the space of these outer products, these hubs and authorities, both within different topics, you get sort of a description of each user and each page. Latent factor models then can be sort of generalized from this SVD, the singular value composition view, to other types of data. I think one of the most famous ones is recommendation systems, where you actually know maybe ratings on individual terms, but there's tons of missing values. I haven't rated a movie on Netflix, so I don't know. Netflix doesn't know how I feel about it. And so if you don't actually have those missing values, you can't run matrix multiplication. That would treat it like a 0. It's a bit different. So you can do this optimization problem of minimizing this function, where you have this squared error on that prediction. So you can say, for example, Kanye West doesn't like the sound of music, right? And so we say the inner product of his preferences across romantic movies and musicals and horror movies compared to what its sound of music's genre breakdown is. And again, you have the same inner product property now, but it's predicting the rating rather than is there an edge there or not. And so one way to view this, though, is that you're creating this reconstructed matrix, M hat, based on these inner products of each user and each movie. Now, pretty much a lot of work has been done sort of taking this concept and generalizing it to even more aspects of your data. So Yehuda Koren had a paper in 2009 KDD that won Best Paper that said, let's add some more terms to that prediction. So at the simplest level, let's just take the general offset of the data. Let's make it so it's zero-centered, right? And maybe each user, maybe some people have a bias for being very harsh or very easy to give like positive reviews or negative reviews. And same for movies, maybe they're generally positive or negative. And so we need to understand what's your relative sort of liking of it. And on top of that, what if we know time, right? So time can say, look, over time on Netflix, essentially, there was some big jump in the average rating. So probably they changed maybe the words that they use to describe what is a 4-star review. Maybe that went from being good to great or something like that. And also for movies overall, interestingly, he found that when the movie was put on Netflix, the average rating went up. So maybe people at the beginning just because knew they want to see it, people later have to actually seek it out and want to see it because they think they'll like it actually. And so you can start to add these terms in now to your prediction that capture more and more latent concepts around it. So this is basically using the time that the review happened, maybe relative to when the movie was released or when just time overall, can get better quality predictions. So there's been lots of work that sort of builds up these different ways of capturing intuition about your data inside of this factorization. Another thing that's been worked on is sort of taking this as an optimization point of view. Right? So we went from SVD, which looked at very sort of this graph eigenvector, really theoretically grounded approach, to the non-convex optimization, where you have to sort of optimize this objective function, to now this Bayesian approach. So the Bayesian says, okay, I have this, think of this bar plot as the values in that vector, that user's preferences. We can say we can now actually look at for every user, their preferences as this bar plot, and sample it from some prior, right? Maybe some 0 prior. And we can actually use some of the Bayesian tools to actually say maybe overall people actually like romantic movies. It's just a positive thing. And maybe the same thing goes for musicals. And do the same thing on the movie side. Have this sampling, right? And so you have this more Bayesian approach to understanding your data. This was worked on by Ruslan, I can't say his last name, unfortunately, and Andre Min. Right? And so you get this prediction, and you believe it's a Gaussian prediction with some error, and you say, well, I want to get the probability of the observation matching this Gaussian as well as possible. So you want to sort of have it fall close to the mean, of course. It's similar to squared error, actually. And pretty much they found this did really well. This is on the Netflix challenge back in 2008. And so we did some work extending this, saying, well, maybe there's different types of people. Maybe some people, liberals and conservatives, sort of have different preferences and biases in terms of the way they rate things. And this creates this sort of co-clustering inside of your factorization, or you might have liberals, conservatives, maybe Greek people, maybe movies by a certain director or IMAX movies, and these sort of will be treated differently based on the category they're in, and so we want to share knowledge within those groups. And you sort of end up finding these groups generally exist, right? You end up saying most movies that are from, let's say, Scooby-Doo end up together, and children's sort of comedies end up together overall. Some more science fiction things end up together in some clusters. And you end up finding sort of generally reasonable categories to share knowledge, sort of so that they sort of share their ratings together in this Bayesian sense. The other interesting thing we found was that most models, where they assume this Gaussian is what the reality is, but let's say hard drives have this actually very bimodal J-shaped distribution. And you can see this is on Newegg for hard drives. They're in apps on the App Store. Yelp, you see there's this restaurant, my favorite barbecue restaurant, has this Gaussian shape. And so we actually create a model that can capture both Gaussians and bimodal sort of J-shaped distributions. And we end up finding, interestingly, is it really depends on your data, essentially. Right? So this is part of sort of, taking these classic tools and sort of making them work with the data you have and your intuition about the problem. So we actually found that within Netflix alone, movies generally have more Gaussian-like shapes, and TV shows are more bimodally distributed, where it's very extremely skewed towards positive or negative. And so we can sort of build up from here. We can go to tensors. Actually, so before we move on to bigger things, let's sort of take a break. Any questions about sort of collaborative filtering generally?
You're talking about Gaussians, but I guess you have a limited friendship there. It's not like a beta distribution.
distribution or something like that?
You're saying Gaussian because it's discretized?
No, and also because it has low state, which in your case you are limited to 1 to 5 stars.
Right. So in most of these models, like the original Bayesian probabilistic factorization paper, they actually don't deal with that fact that there are sort of limits on this. I mean, of course, there's ways you can deal with it after the fact, but I mean, the easiest thing because it's a Gaussian is to treat it as so squared error, which is like sort of what RMSE is computing, is the same thing as saying I want to predict a Gaussian. But as you mentioned, it's really not. It's really a discretized thing that you're predicting, so there's some mismatch there. And part of what we did do actually here was to now switch it over to being a discretized thing you're predicting, actually, not just this unlimited long-tail Gaussian. So there are lots of ways that you can sort of match, again, the problem with the actual model that you're learning. Other questions? Cool. So tensors now look at data that's sort of in more modes, right? So you can think of this as having extra metadata or sort of features on your edges, right? So maybe I know the time an edge was created. So Kanye West rated The Sound of Music 5 stars or 1 star last January. And so this third mode back in the tensor now would correspond to when did the rating happen? And so this tensor decomposition now looks at this three-way inner product, right? It's still capturing these sort of these communities, these of interest, these blocks in the tensor, but you're now doing it across all three of these. And so you say maybe when was there some group that likes something at the same time? So one example we'll look at here looks at the DPLP network. You take this sort of author-by-author matrix, but create edges differently. Some cases, who cites whom. Some cases, who are co-authors. Some cases, based on do they sort of use similar words in their title, probably mean they have similar topics of interest. And can do this tensor decomposition. All right, and make it sparse, which I understand in particular. So there's ways you can modify your objective for that purpose. And sort of we did this on Beutel and Leman and Dino did this on 2 different data sets of DBLP. And you essentially get these block-like patterns showing up. This is sort of course, taking those factors and showing that they sort of come out to these patterns. So maybe this is the first singular vector, corresponds to that block. And this is the next one, this is the next one. So you see these blocks sort of correspond through the tensor in some cases not. And you sort of can capture these different three-dimensional patterns. Same thing goes here, these large block across different components based on citation, co-authorship, and using similar terminology. And overall, this had very good accuracy in terms of predicting these edges. And you can sort of keep building up from here. You can say, well, maybe I know in this tensor I also have side information. So now you have node attributes on top of edge attributes. So the edge attributes put the tensor deeper. Node attributes correspond to a linked joint coupled factorization. So maybe along with knowing sort of the time that Kanye gave a rating, we also know explicitly some side rates for the movie, who produced it, or what the genre was, or what year it came out maybe. And so this corresponds to the side matrix. And now what you do is you say, okay, I want to share this U matrix corresponds to the movie's properties, its latent factors, and that might be used to both predict the ratings in terms of U, V, W for this X matrix, as X tensor, and then also for U times A to predict this matrix Y, right? So you can sort of make sure that the movie's properties are jointly useful in describing both side information and ratings. And we'll see how this ends up being used later for fraud detection. One interesting thing here was a study done recently by Samir and Nitishir. They actually won Yelp's, I think, the third year in a row, prize for analyzing their data. They did this public data analysis contest. And they used all of Yelp's data, which corresponds to this many-way joint factorization. They have things like the business category, review ratings, review text, attributes of the business, and other features. And like sort of which combinations work well. And what they found was essentially, obviously predicting ratings are most important. You have to have that. And you end up seeing that the things that give the most boost are the text comes next in terms of being useful. So it's a joint factorization on both the ratings and the text together. And then the business category. So you sort of can build up these pieces, and you see each piece goes from this sort of underlying baseline of recall and precision of predicting the ratings to then giving this boost based on text and then by category. And so you can sort of build up this quality with more and more data. And so that's, for now, we covered fairly quickly, I think, the information for normal attributes or normal behavior. So any questions for sort of how we've done that? All right, let's move on then. So I think most commonly these methods have been thought of as these collaborative filtering tools. They can be, there's other sort of similar relationships between sort of predicting ratings, predicting edges, predicting communities, and text, and all sorts of things. The question becomes, what happens when there is fraud? How does that show up in these models? Right, so we can have this graph of who follows whom. Maybe I follow Alan Turing and Christos, and there's this group of fraudsters down here. Maybe I get hacked and I start following Dr. Evil and Darth Vader. And the question becomes, if I view it as this factorization approach, and I have this followers by followees structure, approach, I might be able to know here Obama corresponds to these communities, but what do fraudsters look like in this shape, right? We had some intuition from before from, let's say, trust rank or distrust rank that, okay, maybe the fraudster should or should not show up in this first singular vector. But when I have these bigger models that are capturing many different communities, what happens? So some early work found these sort of dense blocks called eigenspokes. And pretty much what they found was if you have this dense block here of followers and followees, like a really tight-knit bipartite core, this corresponds generally to having one of the components being very strongly 1, and then pretty much 0 everywhere else. So it's mostly, or just some small epsilon noise there. So pretty much what you end up capturing is, here's a dense community that's sort of uniquely isolated. This bipartite core that's really not being followed by anyone else. And this is called an eigenspoke, and it's sort of indicative of sort of something odd. It's at least suspicious. Maybe a community that's normal, maybe not. But what we found was essentially looked at Tencent Weibo, which is like Chinese Twitter, and you can find these ray-like patterns, right? So they're not perfectly. They might sort of try to add some camouflage or some other sort of maneuvering to try to avoid creating this pure dense bipartite core, but they still show up as this very odd behavior, corresponding to a sort of staircase-like pattern in the matrix. And so what we end up going back and analyzing, these accounts all end up being very similar. Right? So we only use the graph, the raw static graph for this. But if you go back and look at the side information, you can look at the user name, ended up being always a number, right? So there's a clear pattern, not realistic remotely, and a birthday of January 1st, right? So these are clearly anomalous for some sort of adversarial purpose, and just showing up in the graph behavior. Now, we had this next thought was, well, we're doing this on a limited rank, right? You could run, I guess, the factorization to be of some massive rank, but really you pick usually a relatively small one to capture the major concepts in the graph. What are the top level topics? And so you look at like Twitter, for example. We had a data set from Twitter, and we get the singular values of the matrix for the top 50 singular values. You see sort of levels off at some point. But what you found is that you can create a block here, independent of customers and fraudsters, totally through the rest of the graph, that we can say will provably fall below this threshold. In fact, if you have, given this threshold like around 1,000, if you create a 900 by 900 size block, it won't show up in the top at all 50 singular vectors in this graph. And so this is a problem. If you're trying to use these methods to catch fraudsters, they're just not going to show up anywhere in this top set. And so what we looked for then was cases where they had a very large community. They're doing lots of things, and none of it's showing up in any of the normal behavior that we're modeling, right? So most people show up somewhere there, right? So this is the sort of the classic outlier, right? This is something weird that we have some really large amount of out degree. So they're doing lots of things, and none of it seems normal. None of it's even remotely modeled by our normal model of behavior. And so we pretty much went back and looked at these accounts, and you see they're posting, or this is literally they're posting links to buy followers. So exactly the fraud we're looking for, they're posting links to do that. They have these sort of copy and paste names of SunGuard 55, 56, 57, and other sort of spammy links. And pretty much we did some analysis again with some real people going back, look at these accounts, found it was 93% precise, and most of these accounts were not called by Twitter, even though the data set was 2 years old. Say 2 years from when we collected the data to when we analyzed the data, and the accounts were still alive. So there's still, like, as a complementary method to the first eigenspokes get the scoop sort of techniques, this finds a different set that needs to also be caught separately.
I'm sorry, I couldn't follow how you reconstruct the algorithm.
Oh, that's interesting, actually. So in this case, right, so one way you could think about it is you could do this inner product, right? And you could go and say, well, outer product of these matrices, right? And say, well, in the reconstructed matrix, what's the total sum of these values? The problem is that would be super, super computationally inefficient. But because of some properties of essentially the SVD and the orthogonality of your factors, you can actually look up just the sort of size of these values. You can say, okay, if the sum of the squares of these terms is large, that means that the reconstructed degree here would be large. So you can sort of just take the sum of the squares of these and say pretty much how big is our embedding, our factors, and that corresponds to sort of what we're predicting in terms of the edges. So pretty much if you're predicting nothing, but there's a lot there, that's bad. And that's why you have this reconstructed out degree versus out degree. Is that clear? Cool. Any other questions? All right. So those covered sort of this, again, this no attributes information. We're doing this sort of pure binary graphs. And even there, we can see we can do very well. But lots of cases, we want to sort of be able to disentangle more fine-grained detail based on side information. It's almost always helpful. So one thing we looked at was going back to saying, well, we know maybe there's this group of people, say liberals, that are similar. We have the sense that fraudsters do these certain types of behaviors. They're probably similar, therefore. They're often acting in unison to try to have a bigger effect through these micro actions. So we can go back to this Cobify paper from before and say, look, this co-clustering, we don't actually know what these clusters are. They could be liberal conservative. They could also just be fraudsters, right? And so one nice way to view this is we actually can prove if a fraudster wants to have a big impact, they have to add edges that are different to try to sort of skew the distribution of the ratings. But if they do that, they're going to look different and get clustered together looking different. So you can have some naive spammers, like the eigenspokes pattern, right, of just one really strong vector being all ones and everyone else being like 0. Maybe some spam patterns with some noise in the middle, trying to sort of, this is more like those rays we saw. And maybe some hijacked accounts, right, that were sort of hard to capture a succinct pattern, because there's some normal behavior, but then they get hijacked into something really adversarial and they just seem weird and different. And so they'll be clustered based on how their adversarial behavior is similar to each other. And so you sort of can capture, therefore, all of these concepts are being captured within these factorization methods. And so we did some tests then. We took, I think, the Netflix data, or Amazon data, and injected fraud. So let's add edges that are adversarial bad, just sort of really bomb some products, or really boost up some other products. And we always looked for cases where you had a product that was supposed to be good and we'd bomb it, or a product that was supposed to be bad and we'd boost it up. And pretty much what you end up seeing is that they almost always get all put in the same cluster together. You'll have these groups of users, all the ones that are injected, the naive spammers, they'll end up in the same cluster, as well as the products that they're spamming get put together. And you can even take where you take the worst case, right? You have real accounts that get hijacked and then they start adding spam, and they'll still get clustered together also. It's like the worst case sort of camouflage for them. So that was testing that concept. The next thing we look at is then what if you have edge attributes? So you have this coupled matrix structure. This is some work by Manish Gupta, Jing Gao, and Xiaowei Han. Sure.
In the previous case, mixture clustering or disjoint, like the hijacked accounts will be in the mixture?
So, I mean, there is some probability of ending up in either one, but you can always sort of say they have to be in just one of them. And the results here were actually from saying they're in just one cluster. And they're always ending up in that same one cluster together. So you force them into one based on sampling and things. Any other questions? We're taking a break. Cool. So the next concept here looked at outliers in joint factorization. So we have these two types of data. It's a heterogeneous graph. And we want to sort of be able to do this joint factorization between these, like, let's say, node attributes and the graph itself. They do a bit different formulation here, right? They say there's actually two different matrices of factors, but they should be about the same. So a little bit of them to be separate, but for the most part, they should sort of agree. And we want to be non-negative, so we have some understanding of what's happening in this factorization. There's actually a really interesting design of their matrices here. It's not just raw data, but you can sort of go to the paper, see the details, but the method generally applies for any of these sort of graph structures. So no need to go into it here for now. But the one interesting thing here is they say a factorization is like a clustering, particularly when it's non-negative, right? So each row, let's say, of this U2 matrix corresponds to how much they believe that a column of this V2 represents this row. So you could say that these are like centroids describing these terms. And so what they end up saying then is a given row here of x2 should be close to some of the patterns in here, right? That's what it would mean for it to be modeled well. And so you usually have these well-defined clusters of things that are fairly similar. But what ends up happening in practice is most of the time that's true, and you get these individual outliers that don't really correspond to any of the groups. So while sort of Cobify found groups of users that were similar, this finds individual outliers that are different. And so these can be sort of both different types of outliers or anomalies that can be existing within your factorization model. And so this is sort of this quick overview of these different methods that have started to use how has fraud been sort of embedded in these factorization models, and how can we sort of use these models to understand and disentangle normal and abnormal behavior, as we sort of pushed from some subgraph analysis to propagation methods, and now to these multi-factor models. And again, key here is we sort of built up from just static graphs to having attributes. Also, another point, I put pluses here as a statement of they're applied in these cases to directed or bipartite, but these are all matrix modeling algorithms, right? So you really, as long as you can put your graph in a matrix, which you can, it would work on other types of graphs too. So the recap here is a few main concepts. One, SVD captures these communities of interest with some provable guarantees. Bayesian methods can handle missing values in a wider variety of cases. They're more flexible to sort of adapt to the patterns and anomalies that we want to describe or capture in the data. A group of outliers spotted by Cobify or Get the Scoop can be used for disentangling, right? These methods might get both of them inside of them, and so sort of letting it happen, but disentangling them and pulling them apart afterwards is useful. So that's the high-level concepts from here. And so I'm way ahead of schedule, so we'll go through the conclusion briefly, then we can take some questions or discuss some of the topics. We've gone through sort of a few of the many different ways these pieces can overlap, right? You can have these undirected, directed, bipartite, node attributes. We call it one thing, but of course there's tons of different types of attributes that are useful and each in their own right interesting, as well as edge attributes. Obviously, time and rating interact differently. Some IP addresses are different from maybe country. And then semi-supervised versus unsupervised require different types of understanding of the data. And pretty much going forward, as we have more and more data across more and more companies and interactions and things like this, we want to sort of be able to join these different properties and use them all in a way that sort of captures what's happening in a deep way, while still being able to capture when is there fraud possibly happening. The next big problem is adversarial analysis. This is John Nash. One way to think about it is maybe, is there some stable Nash equilibrium for when we're doing fraud detection and there's some adversarial that's trying to add fraud? Or more generally, what's the worst case analysis, right? In all these methods, can we provide some provable bounds on how much fraud can be added before alarms are set off in a given data set? For it to be relative to whatever the normal behavior is for this outlier, we should still be able to understand that for a given data set or given problem. And finally is early detection. Some of these methods do look at sort of a subset of the data, but most of them really just say we have this static graph, let's do the analysis. But in many cases, we want to sort of detect the methods, the adversaries' methods, the fraudsters, before they do too much damage. Once they've done the damage, well, it's sort of too late. In some cases, that's okay. In some cases, it needs to be right away. And so how can we sort of use early signals in the graph, the first few connections, to catch them and remove them as soon as possible? So these are big open problems that will take probably a whole thesis worth of work. So the three high-level topics, again, local subgraph analysis captured just general patterns among local groups of the graph, modeling them and finding anomalies within those subgraphs. Propagation methods used to sort of guilt by association, importance by association, which like PageRank, to find these patterns. And ultimately, then we looked at, as you build up from single communities to multiple communities, understanding the patterns and the anomalies within them and amongst each other and relative to each other. Again, the key takeaway that I want to stress is the whole goal here was to look at the relationship that these are the same methods. They're used for both modeling normal and anomalous behavior. and often people think of it as one or the other. Really, it's a joint problem. You need to understand both of them to do well on either of them. As we said in this case before, it's about saying which is normal, which is abnormal, what is an outlier to us. And doing better on one will help the other. And so trying to sort of merge these, people who work on one, bring their ideas to the other, I think will be very valuable. And with that, there's a workshop after lunch and in the morning, but it's too late now, on outlier detection. There's an interesting panel about what is an anomaly, sort of exactly this question, what's an anomaly versus an outlier versus fraud. And so go see it in the afternoon. Again, thanks to all the funding agencies that contributed. And now we can take some time to answer any questions.
Can you talk a little bit about the computational scaling issues and when you get to 1 million nodes or 10 million nodes or 100 million nodes?
Yeah, it's a really interesting big problem. I'd say that there's a few, it depends on the method, right? Subgraph analysis, if you're doing like ego nets, that's inherently parallelizable, right? Each ego net is independent. If you're looking at propagation methods, I mean, this has been around luckily for 10, 20 years, and lots of work has gone into doing these sort of scalable matrix operations of matrix multiplications, and when it's sparse, as it almost always is, it's efficient. The last one, though, in terms of latent factor models, I think is still getting a lot of attention, particularly in this like now big learning communities, methods like GraphLab, Pegasus. They all look at sort of, if you want to do optimization, whether it's sort of gradient descent-like methods or Bayesian optimization at scale, how do you distribute that over the many nodes? And all of these methods sort of aim to, for one, obviously only work on the observations, on the number of non-zeros, and be scalable in terms of that. The second big thing is sort of, these methods are all inherently about the interconnectedness of your data. And so you need to be able to find independencies, right? So in the propagation methods, the nice part there is that their propagations are messages being passed between individual nodes, and so each message can be handled independently and in parallel. So that's things like Giraffe. It's an Apache system for that. I think it's Pregel was what Google published on that. In terms of factorization, you now have this sort of interdependence in this quadratic way. And so you can get these sort of block-like patterns to do different parts of the matrix in parallel. And so lots of work now is looking at sort of how can you sort of exploit both the sparsity and the structure to scale up these methods over these billion nodes graphs, which Facebook and Google do all the time. But it's a continuing problem as the data grows bigger and bigger.
That's a very good answer. Let me go close to the microphone. And in addition to what Alex said, one promising direction is also what Vangelis, the gentleman in the front row, is doing, triple sparse method. So the initial graphics, the initial matrix is sparse, that's good, but the standard methods usually give dense vectors as the end. The page rank vector is dense, or the first singular vector is dense, right? And often the intermediate results can be dense. So Vangelis Papalexakis is working on algorithms which will have sparse intermediate results and sparse final vectors. Without the standard method to find sparse final results is find the dense result and then start deleting values, right? The idea is to not do that and go directly for ask for sparse vectors to begin with. So, yeah, there are a lot of details that we can discuss offline, but scalability is a big issue. And as Alex said, the fact that matrices are sparse helps a lot to keep them scalable. And we can do even better than that, too. Good question. Thanks.
And I'm just going to add to, I think it's fair to say that everything we discussed here is more or less scalable because all these methods are coming from the data mining community. So especially for the global methods like propagation and the factorization, most of them are linear in number of edges. And for subgraph analysis, most of the methods are local, so sublinear, not looking at all the graph, but really looking at finding subgraphs in a more, not looking at all the graph, starting from somewhere and maybe doing a local source, so they're mostly scalable, sublinear, thanks to the data mining community mainly being aware of the scalability issues in graph algorithms. For instance, for factorization, there are other factorization approaches that beyond SVD, right? Just SVD produces really dense U and V matrices, but there are other factorization approaches that actually sample rows or columns from the original A matrix, adjacency matrix, to build up a reconstruction so that not only the reconstruction is good, but the U and V matrices are also sparse. So there are other approaches that pays attention to that.
How do the tensor methods scale?
Yeah.
How do you optimize in those cases?
I mean, so a lot of it is a similar challenge as the matrix factorization approaches, right? There's still often these optimization-based solvers, whether it's ALS or SGD. I think the interesting part there is that you have possibly more sparsity. There's more cells for the same number of observations, but the interconnectedness is more, right? You now have this three-way interconnectedness. And so depending on your solver, you have to sort of handle these in different ways. But I mean, ultimately at the core, the methods like ALS do scale very well. And there's ways to, again, find ways to parallelize it. So I think it's both very doable right now and also at the same time an active research area to do better. And another thing I want to add is that like a lot of what we focused on, or we aimed to focus on, was sort of the ways in which your intuition about your data can let you change these methods. And sometimes those changes become less scalable. And there's sort of this back and forth pull of saying, well, let's try to make our method match the application, and then let's try to make sure that that is also scalable. And so there's this sort of back and forth of let's build these up, new tools that we believe are right, and then let's sort of scale them to our problems. I think they're sort of moving hand in hand right now, which is exciting.
So in the matrix factorization, you mentioned that there was a binary matrix, that you have interaction or not, and you have the review matrix, that you have some 0-1 rating.
Sure.
Is there work now on counts matrix, so where I don't have a review or a binary, but I have a number of interactions?
Yeah, it's a huge area. So lots of oftentimes text is thought of this way, right? Because text is the, say in a bag of words model, say the number of times a word was used in a document. This is typically thought of, I mean, there's lots of ways this is approached. One way is to think of it like a Poisson distribution, which is better for the sort of discrete number of counts. Other times you can say take the log of it and do the normal optimization with a squared error. So different sort of techniques handle it differently. But I think overall, this is definitely a big area with different people using different approaches depending on the data set. Another one that's even more complex but exciting, and I think one of the big open problems in this area is in, let's say, the Netflix case, right, where you have these ratings. We treat let's say, the question of what is the missing value, is it a 0 or is it not there? Right? I think it really is this joint question of, well, is there an edge? If there was an edge, what would the rating be? And so they're doing this thing jointly and sort of handling these problems as, it's a binary statement with the rating statement. And you sort of build up these larger and larger questions of what goes in these cells or what's happening in these interactions. So you have multiple maybe attributes. Is there an edge? Maybe what's the rating on the edge? What's the text on the edge? What words were used? Things like that. So you have actually this multi-way, many aspect relation.
One short question. What's the bad rate for your sample data?
Sorry,
What's the bad rate for your sample data?
bad, right?
Bad.
Target rate, the fraudsters. How many fraudsters are in your data?
It depends on the data set, honestly.
I don't think anybody knows.
I saw some of the data you have like from 40% maybe. Is it like not for spam problem?
So I mean, I've seen numbers. I know that, like, for example, in Facebook's IPO, they claimed 10% of their accounts were Sybil, so fake accounts. I've seen Yelp studies that range anywhere from 2% to 30%. We looked at Tencent and Weibo, and we have some numbers there of, like, out of our data set, what do we find? How many are in these dense clicks? But we don't have, of course, quite the same resources to do a really thorough labeling. It really depends on, I think, the data set and the domain, the money involved in that, how much incentives there are, et cetera.
And even worse, nobody knows the exact rate because nobody knows who is exactly a fraudster, right? We run the algorithms, we catch a few guys, who knows how many we missed, right? And not even Facebook or Google knows how many they're missing, right? So that's a very, very good question, very tough question we are asking, yeah.
And if you paid attention to these tables, we had these seed labels. Almost none of the methods we introduced actually use seed labels. That means that all of them are unsupervised or at best semi-supervised. That means we don't have labels. So the way it works usually is like you report top K and maybe look at, rank them somehow, and I look at them. So you can only have an idea about precision. Recall is usually unknown.
But you have the PR curve.
Right, so
So you should
in-
lose some percentage of the.
in some cases we do, right? And usually it's a question of what are we defining as the fraud we're looking for? And so you can do different techniques to try to do it, right? Say, let's sample accounts randomly. I think to get truly recall is hard, right? Like, this is part of, I think, the question of what's an outlier, or what's, like, do you want to do fraud detection or outlier detection? But say, okay, we believe this pattern, we've caught all of this pattern. It's an NP hard problem, but we believe through sampling we've done a good job on it. That doesn't mean that there aren't other patterns that we've missed that are still fraudulent. And so I think this is why you need some more adversarial analysis to try to really prove, in the worst case, what's happening under the right sort of abstractions. Any other questions?
Most of the examples in this case, this user, this product or web page or whatever, they have links, for example, thumbs up, thumbs down, or or different comments with opinion. You can know, whether, for example, the user favors or against the product. But in a scenario like this, for example, if we have many different clients, and the clients they have their contact, email address, or living address, all those kind of things. If we based on that, for example, two clients they share same contact, same phone numbers, or same email, then we build a link between them. If we construct such a graph, it will be different from what we construct from social media. In that case, do you think it's possible, for example, we do some analysis, for example, because historical, we have some high risk cases, can we use, for example, something like a risk propagation or whatever, belief or whatever propagation to infer or predict high risk cases? And do you guys have studied apply your method on data set like that?
You want to repeat the question?
Okay, so the question is, what if you have users, but also you have side information, like what if they share a phone number or social security number and things like that? How can you integrate this?
What I mean is the links are based on, for example, they share some attributes, not necessarily, you sum up or sum down to a post or whatever web page.
Yeah, so that made me think about approaches to fraud or anomaly detection in heterogeneous graphs. So people have looked into representing these things as heterogeneous graph, where you have user nodes, but then you have maybe social security nodes or phone number nodes, and then whenever a user exhibits these attributes, you put an edge, right? And then in order to do, for instance, in this part 2, when Christos was about belief propagation or label propagation, people have defined graphs between users through what they call metapath. A metapath is basically a type of a path between two users. For instance, user, phone number user, or user, SSN user, right? If they share, that becomes a different type of path. And based on each different type of path, you can create a unified graph, user-user graph. You put an edge, how many metapaths of that type do these users have. Then you can have for each metapath different graphs and do a maybe join or semi-supervised learning on this multi-graph. People have studied this, and that reminded me of a heterogeneous graph representation.
And along these lines, a simpler method, that's the right way to go about it. A simpler method that was actually used in accounting, PricewaterhouseCoopers KDD 2009, there was a system which says that if two people live in the same address, they're both a little bit suspicious. If they both have the same number, they're a little bit suspicious. Not enough to alert, but suspicious. And then with belief propagation, the accounts that these people are touching are suspicious. And then this way we can combine the weak signals, same address, round numbers of amounts, right? If I send a check of $300, that's suspicious. Usually checks are $299, $376, right? They're never 300 straight, right? Or if our divisors of a big amount, suppose I want to send you $1 million and this is illegal, so I'll split it in 3 amounts, right? So first and third. So if there are all these weak signals, they can be combined with belief propagation, and then the belief propagation will pinpoint the top 2, 3, 4 most suspicious accounts, most suspicious people, right? Also very good question, thanks. I think that's it.
Sure.
We'll be around for more comments if you want, for discussion.
Leman's organizing, so.